Hey guys, welcome back. I want to do another video on organic chemistry. We're going to start off with, we've already talked about structures. We've already talked about Lewis structures, geometries, hybridization, different pi bonds, sigma bonds, how to analyze that. We talked about using line structures. We talked about then thinking about line structures as in terms of uh, resonance structures, how to examine resonance structures, how to think about the priorities of resonance structures, how to use arrows to change between resonance structures. And then we're going to take all that stuff and we're going to apply it into sort of the first bit of thinking about actual chemistry with those tools. And the first thing that we think about typically with those tools in organic chemistry is acid-base strength. And so what I want to do today is I want to talk about Bronstead-Lowry acids and Bronstead-Lowry bases and a quantitative view of those acids and bases. How do we look at actual numbers, specifically PKA and Ka values, in order to determine that? And so it'll be pretty short and sweet because it doesn't involve a lot of detail with the qualitative, as much detail as the qualitative stuff. The quantitative stuff really does take experimental evidence, and you're not going to necessarily have that at your fingertips. You'll have to reference charts. And so when we get to talking about PKAs, we'll dig into that just a little bit more. But first, let's move into kind of talking about or getting an idea of what we mean when it comes to Bronstead-Lowry acids and bases. Okay, when I get into acid-base definitions, there's two of them that we're going to deal with. And right now I'm talking about the Bronstead Lowry acid and base. Bronstead-Lowry acids and bases refer to acids and bases specifically in terms of their ability to donate and accept protons. So a Bronstead-Lowry acid is a proton donor, and a Bronstead-Lowry base is a proton acceptor. And so what are some examples of Bronstead-Lowry acids? Well, you know, any of your typical halogen-based acids. I'll keep writing X. Any of these oxo acids that you're familiar with? There's the 7 strong acids, but any of the weak acids are also considered Bronstead-Lowry acids. Some of these protonated species that you're familiar with, that's certainly a Bronstead-Lowry acid. Certainly NH4+ is a Bronstead-Lowry acid, and even water can be considered a Bronstead-Lowry acid because it can form hydroxide ion when it donates a proton. Bases, Bronstead-Lowry bases, are typically things that have lone pairs of electrons, like ammonia, hydroxide. It doesn't necessarily have to have a charge, but it has to have some electrons to accept protons with. And so another example would be a pi bond, because you could take a pi bond, you could react it with H2 and form an alkene. That would be an example of a pi bond acting as a base. Strictly speaking, it's an addition reaction, but you are donating a proton to it, in a sense. So, you know, you can think of it as a base. I think some folks are going to argue with me and tell me that's an addition reaction. It's not really acting as a base because it's not really accepting a proton. And I would say, okay, you're probably right about that. But at the end of the day, I can use a double bond as a base. I can accept a proton. If I do an addition reaction of HBr, there is an intermediate carbocation that's formed. And while, since that was a proton transfer, that certainly was a step that could be considered that acting as a base. And so what's the difference between Bronstead-Lowry acids and bases? Just the difference between proton donating and proton accepting. But you got to keep in mind that a species can be both a donor and an acceptor. We already talked about water. Let's talk about NH3, right? It could definitely be an acid and donate a proton. Have you ever heard of amide ion? If this is it acting as an acid, or it can be a base and accept a proton and form NH4 plus. And so, of course, all the conjugate bases of these ions, so nitrate could be a base, even though it's very weak. Sulfate could be a base, even though it's very weak. The hydrogenated versions of these things, hydrogen sulfate, could be a base as well. And so anything essentially that has a negative charge or lone pairs can act as a base. All right, so when we take these Bronstead-Lowry acids and bases, where do we ultimately we want to get at an idea of what their strengths are. And so how do I wrap my head around the relative strength of a Bronstead-Lowry acid or a Bronstead-Lowry base? Well, the first thing that I want to be able to do is write these reactions down. And so let's think about where we have water reacting with itself. We did this in general chemistry too, and it forms H3O plus and hydroxide ion. Well, it's arbitrary at this point, but you could say that one of these is acting as the acid and the other, oops, backing that up. Again, it's arbitrary. One of them is acting as the acid and one of them is acting as the base. With Bronstead-Lowry acids and bases, you always have a conjugate. They always come in pairs, conjugate acid-base pairs. So this one would be the conjugate acid, and this one would be the conjugate base. And because it's an equilibrium, and it's the equilibrium associated with water, we call this equilibrium in particular, KW. But we can write this hypothetical reaction where we have a hypothetical acid, and it can donate a proton and become H plus and whatever A is, A with some electrons, and in this case it would be negatively charged. This has an equilibrium constant. It's an equilibrium reaction. It's got a Ka, and I can write down the Ka, the equilibrium expression, as the concentration of H plus times the concentration of A minus divided by the concentration of HA at equilibrium. And so, you know, we did a lot of stuff with this in general chemistry too. We took the log of both sides, and then we came up with the Henderson-Hasselbalch equation. But at the end of the day, this is a measure of the strength of the acid. The better it is at donating the proton, the larger the concentration of H plus will be, so the larger the Ka will be. Now, what does that mean as far as the values of Ka are concerned with in different acid strengths? Well, there's actually quite a range of Kas. The range of Kas for acids start on the high end at around 10 to the 9th, something like that, 10 to the 10th. And on the low end, it's like 10 to the 50th or something like that, 10 to the negative 50th. And so one of the things that I try to point out to my students is that this is 60 orders of magnitude. And if you go out and you look up the entire size of the observable universe in terms of meters, let's see, observable universe in meters. It's like 46 billion light years. put it in meters. Here we go. It's observable universe. I'm talking about the entire universe. It's let's just round up. It's 1 times 10 to the 27th meters. What about the smallest particle in the universe, or one of the smallest particles? Let's use a quark. I think they're on the order of 1 times 10 to the negative 18th meters. And so what's this in terms of orders of magnitude? This is essentially 45 orders of magnitude. So this is an interesting piece that I like to point out to my students. What I'm saying, what these numbers are telling us is that the vastness in the difference of acid strengths is about 15 orders of magnitude larger than the vastness between the size of the smallest particle in the universe and the size of the entire universe. So that's a huge difference in acid and base strength. And so one of the things that we typically do when we talk about the strengths of acids is we typically talk about the pKa. And so remember that the pKa equals the negative log of the Ka. So when the Kas are, so what do you have? So a log of 1, that equals 0. So the negative log of 1 is still 0. So a pKa equal to 0 means that the Ka is equal to 1. So this isn't some of the strongest acids that we have, but that's what the pKa would be. If we have the pKa of one of the strongest acids, it would be negative 10. The pKa of the weakest acid would be 50. And so what does this mean? This means more negative the pKa, smaller, stronger the acid. And this is important when we're remembering to think about basicity, because basicity is exactly the opposite. A strong base, that's the conjugate of a very weak acid. And so what's a weak acid? Again, it's one with a very large or very positive pKa. So you can get a handle on basicity the same way that you can get a handle on acidity by looking at the pKa. It just, the trend is in the opposite direction. Where the strongest acids have the smallest pKa's, the strongest bases have the largest pKa's. And you can prove this to yourself when you think about a conjugate acid-base pair. If you think about the pKa times the pKb, they always equal Kw. And you can do some algebra there to convince yourself that if the Kw is 1 times 10 to the negative 14th, how those things kind of work out with each other. Okay, and so what does that mean for us, though? So when we think about the pKa's, we really need to get a handle on what some of these pKa's are. Now, in this course, I don't think you should necessarily memorize what all of the pKa values are if possible. You can look all that stuff up, but it's certainly beneficial to know a few of the different pKa values. That way you can get a handle later on of different reaction or different acid strengths when you're presented with them. Now, in another video, we're going to talk about using a qualitative analysis of molecules in order to assess relative acid and base strength But at this point, we're just talking about the quantitative method. And the quantitative method, again, is all about the Ka. Remember, that's the concentration of H plus times the concentration of A minus divided by the concentration of HA at equilibrium. And so if you think about some of the strongest acids we have, we've got H2SO4. It's probably one of the stronger acids that we can deal with. It's got a pKa value. So here, let me list this down. Acid. It's got a pKa of -9. So it's really strong, right? And what about this? We could get a protonated carbonyl group. Here's some different functional groups at this point that you should be familiar with, or at least starting to become familiar with. -7.3. What about good old HCl? It's got a pKa value of -7. Let's think about how about good old H3O plus? We saw that one in the equilibrium reaction with water. It's got a pKa value of -1.7. Well, now we start to get into some positive pKa values. What about something like a carboxylic acid? What's its pKa? They're around 4.7. If we get into some different things, let's think about water. What's the pKa of water? 15.7. What about a typical alcohol? They're approximately 16. What about, let's see, let's do an alkyne. What about an alkyne? How can I make an alkyne an acid? Well, if you pop off that proton, and it's a proton donor, then you would act as an acid. So the last one I would write down would be ammonia, NH3. It has a pKa of approximately 38. And so if you were to think about these species, I wouldn't say let's memorize all of them, but there's some things you should definitely know. I would say to know the pKa of the carboxylic acid, know the pKa of water, know the pKa of a typical alcohol, and know the pKa of ammonia. Because you can take ammonia and you can relate it to groups like this, RNH2 or R2NH. You know, all of these essentially are approximately 38. Same thing with alcohols. The strongest alcohol is about 16. The weakest alcohol is about 18. So the range of acid strengths from alcohols are 16 to 18 in the pKa scale. In other words, water is always a stronger acid than any single alcohol. A carboxylic acid is significantly stronger than water as an acid than neutral water is. Once you start talking about all this other stuff, all you really need to know is that their values are negative, and so they're really, really strong acids. At the end of the day, that's really all you need to do. Familiarize yourself with this chart, and if you were going to memorize something, memorize these 4 values that I've included there at the bottom of the screen. All right, so there's really only one other thing that you can do when it comes to using these values. What we can do is we can take these pKa values and we can use the pKa value to predict the position of equilibrium. And so this is what I want to do. Let's take a look at these pKa values and see if we can predict the position of equilibrium. Let's use the information that we have. Let's go over here. Let's come up with a different color, and let's think about a reaction like this. What if I have H3O plus and it reacts with NH3 and it forms NH4 plus H2O? Well, let's think about this. Remember, they come in conjugate acid-base pairs. So the first thing I want to do is identify the acid on this side, on the reactant side, and identify the base. Then I can identify its conjugate acids and its conjugate base. All right, well, the question I have now is, where does the equilibrium lie? And we know that from our studies that H3O is the strong acid in aqueous solutions. So from that information, we can predict that the equilibrium favors the products. But what if we don't have something where we're dealing with H3O plus? What if it's something that isn't familiar to us and we have to sort it out in a different way? Well, let's take a look at a different reaction. What if I have water and I'm reacting it with an alkoxide ion and it forms HO minus plus this alkoxide or this alcohol? In this case, this is acting as the acid. This is acting as the base. This is acting as the conjugate. This is the conjugate base of the water, and this is the of the acid, and this is the conjugate acid of the alkoxide. Now, let's take a look at this. How can I predict the equilibrium here? It doesn't have something familiar like a strong acid like H3O plus or H2SO4 or HCl in order to say, hey, clearly the equilibrium favors the side that has, the direction where the strongest acid is pushing. But here's something we could do. We could say, is this reaction favoring the reactants or is it favoring the products? Well, we can take a look at those PKA values and we can say, well, what is the PKA? The PKA of water is 15.7. The PKA of a typical alcohol is around 16. Both of these things are definitely bases. They don't have protons to donate, so we don't even have to think about them as acting as acids. Okay, so what's going on with this? Well, which one is stronger? The acid that's stronger is water. It has the lower pKa. The acid that is weaker is the alcohol. It has the higher pKa. And so if we were to think about it, then that means that the water is more able to proceed in the forward direction as an acid than the alcohol is able to proceed in the backwards direction as an acid. Therefore, the equilibrium favors the products in this case. Okay, so the equilibrium favors the products. So what kind of generalized rule can we make out of that? We could say that an equilibrium favors the side of the reaction that has the weakest acid. And so we can kind of bear that out with our previous example. Let's take a look at that example we just used, and let's think about, let's go back to H3O plus NH3 goes to H2O plus NH4 plus. Well, we have to think about what's acting as an acid on each side. On each side, this one is acting as the acid, and on this side, this one is acting as the acid. This is the conjugate acid. The pKa here is negative 1.7, and you don't know this to figure this out. The pKa of ammonium ion, this pKa is around 9. So if you look this up and you find out that the pKa of an ammonium ion is around 9, then that means that it's the weaker acid compared to the H3O plus. So that means that this reaction favors this direction. And remember, it's the H3O plus and the NH4 that are collectively acting as the acids, whether or not you think about the forward reaction or the reverse reaction. Ammonia is not acting as an acid. NH3 plus is not giving up a proton. H2O plus is not giving up, or excuse me, water neutral is not giving up a proton. So we can take a look at these pKa values, and we can write all sorts of different possible reactions and think about whether or not the reaction favors the products or the reactants. Let's take a look at something like this. Let's have H3O plus produces this thing plus water. Well, remember, let's identify the acids on each side and then consult our pKa table. Well, in this case, this is the acid, and in this case, this is the acid. So what have we got here? We've got the pKa of water, or H3O plus, is negative 1.7, and the pKa of this protonated carbonyl group is even lower. The pKa of this is equal to negative 7.4. So which direction does this reaction favor? Does it favor the products, or does the reaction favor the reactants? Well, remember, the equilibrium will favor the side of the reaction with the weaker acid. Once we've identified the two acids on either side, then we know that the other things are, first of all, their bases or conjugate bases, because they're doing the proton accepting, either direction you're thinking about. And the equilibrium favors the side with the weakest acid. Well, what's weak between pK of negative 1.7 and negative 7.4? Well, this one is weaker. So the reaction actually proceeds more in the reverse direction than it does in the forward reaction. It's reactant favored. So another thing, the final thing that we would do, another way, that kind of the last bit of this particular quantitative analysis, is to look at something like this. We could say, actually, let's use hydroxide instead of ammonia. So what do we have? Hydroxide and water, because you can get this right off the list. So one of the things I'm going to do in organic chemistry is ask you a question like this. Is hydroxide a suitable reagent to form the alkanide ion. And the alkanide ion is this guy. All right, so let's take a look at our, let's identify each thing as being an acid or a base. Well, it looks like this thing is donating the proton to the OH. So this is the acid on this side. That makes this the base. This is the conjugate acid. And this is the conjugate base. Well, remember, this is a quantitative analysis, so we do have the pKa information. So we can look that up. It's 15.7 here. And the pKa is, what is this one? This we said this one was 25. pKa is 25. Well, so which one's stronger and which one's weaker? This is the stronger acid with the lower pKa. This is the weaker acid with the higher pKa. So this reaction is reactant favored. This reaction is reactant favored and not product favored. So even though it's an equilibrium, there's quantities of all of the reactants and products in the solution. There's vastly more reactants than there are products. So the answer to the question, is hydroxide a suitable reagent to deprotonate or to form the alkanide ion? The answer to that question is no. Let's take a look. Let's get rid of hydroxide. And let's say instead of hydroxide as the reagent, let's use another base. This one is called amide. NH2 minus. Is NH2 minus a sufficiently strong base to form the alkanide ion? So let's examine that reaction. So if it's NH2 minus forming NH3, it's a different situation altogether. This is still the acid. This is still the base. This is the conjugate acid. And this is the conjugate base. And now we can take a look at our pKa values. And once we've identified the acids, we can assign their pKa values. This one's 25, and this one's 38. So this one is the weaker acid. This one is the stronger acid. And so we know that the position of the equilibrium favors the side with the weaker acid. So in this case, the reaction is product favored. So the answer to the question, is amide a suitable reagent to form the alkanide ion? In this case, the answer is yes. In the previous case, the answer was no when we were using hydroxide. And so that's about the limitation of what you can do when it comes to the different acids that you can run across in organic chemistry, and there's quantitative strength. Remember, quantitative means we've actually got the number down. And so if you think about the number, you have to know the pKa. If you know the pKa, then you can easily figure out how the relative strengths of the individual acids are, whether it's strong or whether it's weak. At the end of the day, you're really not going to have pKa's available to you. Now, that's why I said it's certainly helpful to kind of be familiar with those groups, because that'll be the groups that you'll run across them often, and you'll be able to quickly sort of do an assessment based on some quantitative values. But at the end of the day, you're going to have to use a lot of qualitative analysis, and that's what we'll pick up with in the next video. See you guys later.